In this video, we're going to learn about Taylor series. And before we start discussing those, let's first recall the nth degree Taylor polynomial for a function f of x centered at x equals a. So we defined that as I've written in the first expression of t sub n of x here. So we see how it depends on knowing the derivatives of f evaluated at a, at least up through the nth derivative. We can also express that in sigma notation as the sum from k equals 0 to n of the kth derivative of f evaluated at a divided by k factorial times x minus a to the k. So just as a refresher, let's consider an example in which we find a Taylor polynomial. So we're going to let f of x here be the function 1 over 1 minus x. We want to find the nth degree Taylor polynomial for this function centered at x equals 0 for n equals 1, 2, 3, and 4. So in finding the Taylor polynomials, what I have to do is find up through the nth derivative, especially evaluated at the center. In this case, that's 0. So we start with the function f of x, which is 1 over 1 minus x. I'm going to write it as 1 minus x to the negative 1. Evaluating that at 0, we get 1. I'm going to need to know up through the fourth derivative, so I'll look at that now. The first derivative of this function is 1 minus x to the minus 2. Note that I had to use the chain rule there, so while I brought down the exponent of negative 1, I multiplied by a negative 1 from the derivative of 1 minus x. So those negatives cancel. Plugging in now x equals 0, I get 1 yet again. The second derivative then is 2 times 1 minus x to the minus 3. And every time I'm using the chain rule, these negatives are canceling, so I'm always getting a positive coefficient. So here we get 2. The third derivative would bring down a negative 3 times negative 1, so positive 6, 1 minus x to the negative 4th. Evaluating that at 0 gives me 6. And finally, the fourth derivative would be 24 times 1 minus x to the negative 5th. And that would give me 24 when I evaluate that at 0. So in answer to the question here, I can find the requested Taylor polynomials. So t sub 1, so the first degree Taylor polynomial, would be 1 plus x. T sub 2 would be 1 plus x plus, let me write this, plus 2 over 2 factorial x squared, which is just 1 plus x squared. And as I'm constructing the higher order polynomials, I'm taking advantage of the fact that I can use the previous polynomial and tack on one extra term. So we've already seen the simplification of the first 3 terms to this. Now I'm going to add 6 over 3 factorial x cubed, but that reduces to a coefficient of 1 on x cubed as well. And then finally, the fourth degree, again, I would add up everything from the third degree. And now I'm going to tack on 24 over 4 factorial x to the 4th. And again, that reduces to just having that extra term being 1 times x to the 4th. So one of the things we observed is that for Taylor polynomials, if I increase the degree n of the polynomial, then my approximation of the function f of x improves. So that would indicate that to get the best approximation, we would want to choose n as large as possible. And in particular, what if we tried to send n to infinity? One thing that happens is that this is no longer a polynomial because we don't have a finite degree of our so-called polynomial. But I can take advantage of my sigma notation, because if we start to talk about the possibility of sending n to infinity, in sigma notation, that's just going to affect that upper value for the index k. Doing so yields what we call a Taylor series. So when we talk about the Taylor series for a function f of x, once again, we have to specify a center. So if I say it's the Taylor series for f of x centered at x equals a, I'm going to write exactly my sigma notation for the Taylor polynomial, but instead I'm going to make it an infinite sum. So this would be the sum from 0 to infinity of the kth derivative of function f evaluated at a over k factorial times x minus a to the k. Notice that we can now view Taylor polynomials as partial sums of the Taylor series. And we can start to think about constructing Taylor series using a very similar approach to what we did in finding Taylor polynomials. Of course, at first glance, it seems like this would be a very difficult task. It's implying that we need to find infinitely many coefficients. However, we can approach this by trying to look for a pattern. So if I come back to what I was just looking at, so the function is f of x equals 1 over 1 minus x. Suppose that our goal now is to find the Taylor series for the function f of x equals 1 over 1 minus x centered at x equals 0. So we've already found several derivatives, and I'll point out that from the pattern observed above, we can try to write what we think the kth derivative of this function at 0 would be. So let's come back to this so-called pattern. So I'm not focusing on the part before my arrows here. I really only care what I noticed about these derivatives evaluated at 0. So notice, as we had when we simplified, I'll start at the bottom here, we have 24. Well, that's 4 factorial. 6 is 3 factorial. 2 is 2 factorial. 1 is 1 factorial. And it's also 0 factorial. So I can now start to observe the pattern. It looks like when I evaluate the kth derivative of f at 0, what I get is k factorial. So that is what I'm observing there. So realistically, we can't find infinitely many terms, but I'm trying to notice a pattern. So now, if I take that, I'm going to come back up to my definition in the Taylor series. And what you should notice is that once I know the center, and plug that in for a, for any function, what I'm tasked with finding for the Taylor series is simply exactly the kth derivative evaluated at 0. So we've just observed a pattern here. I'm saying that that is k factorial. So the Taylor series then for this function centered at 0 is, so I'm going to put in the parts that I can't change. So as soon as I have that it's centered at 0, I know it has to look like this. What I have to do is replace this box for my particular function, and that's where I'm going to plug in this k factorial. Notice that the k factorials cancel in this case. X minus 0 to the k, I can just write as x to the k. So our final answer here is simply the sum from k equals 0 to infinity of x to the k. This is the Taylor series centered at 0 for the function f of x equals 1 over 1 minus x. Just a small note, the textbook refers to Taylor series centered at 0 as the Maclaurin series. I will always call them Taylor, but if you're working through homework problems and you see the phrase Maclaurin, note that that's just a way of saying the center is 0. Now, looking at this series, hopefully this looks familiar. We have an x raised to the index k, and so this is, in fact, a geometric series. Of course, the difference here is instead of having like 1/2 to the k or 2/3 to the k, we have a variable x to the k, because this is, in fact, I'll point out, this is also a power series. So coming back to what we've seen before, I'm going to point out that a power series is a series of the form sum from k equals 0 to infinity of c sub k times x minus a to the k. So looking at the power series, let's scroll back up to our definition of the Taylor series and notice some similarity. And in particular, we're going to be able to say here that the Taylor series of function f of x centered at x equals a is a power series with coefficient c sub k equal to the kth derivative of f evaluated at a over k factorial. Notice that the power series has the coefficient c sub k sitting in front of x minus a to the k. If I come back to my definition up here, this is exactly what I have sitting in front of x minus a to the k. So what I want to point out is that this leads to an important fact. Every Taylor series is a power series. It's just a power series with a very specifically defined coefficient c sub k. The advantage of this is that everything we've studied with power series therefore holds for Taylor series. In particular, we've talked about the notion of a radius and interval of convergence for a power series. This means that Taylor series likewise have both a radius of convergence and an interval of convergence. So when we're looking at our example, yet again, that we've studied so far, I can say find the interval of convergence for the Taylor series of the function f of x equals 1 over 1 minus x centered at x equals 0. So what we've observed before is that to find the interval of convergence, we first need to find the radius. And to do so, we need to use the ratio test. So I have my series. Remember, it's just the sum from k equals 0 to infinity of x to the k. So the k plus first term would be x to the k plus 1, divided by the kth term is x to the k. This just simplifies to the limit as k approaches infinity of absolute value of x. And of course, that's constant with respect to k, so this just becomes absolute value of x. The ratio test tells us that this converges whenever our limit is strictly less than 1. And this already puts me into the form of x minus the center less than something. So this tells me that the radius of convergence is 1. In this instance, our center is 0. The radius is 1. So pushing out by a distance of 1 on either side gives me endpoints of minus 1 and 1. If I want to check my endpoints now to see if I have convergence or divergence, we take each of those values and plug them back into the original series. So again, my original series here is the sum of x to the k from k equals 0 to infinity. So if I were to plug in minus 1, that would yield the sum of negative 1 to the k from k equals 0 to infinity. And this series diverges. You could either reference the test for divergence or note that it's geometric with r an absolute value equal to 1, whereas we need it to be strictly less than 1 to get convergence. If I plug in positive 1, we're going to get a very similar result. This too diverges. One way to justify that is because it is also a geometric series with r an absolute value equal to 1. So we've seen now that both of the endpoints cause our power series to diverge. So the interval of convergence here would be -1 to 1, where we do not include those points. And what I'd like to compare this to is what we saw with geometric series. So we're seeing that the sum of x to the k from k equals 0 to infinity converges whenever x is strictly between -1 and 1. But notice that x is playing the role of r in geometric series, and that's exactly the same restrictions we placed on r. So we didn't really learn anything new with this particular example. However, what we'll start to see is that this power series is going to allow us to consider lots of different values of r that we could plug in and get several different, infinitely many geometric series by using that. And further, we're going to consider lots of different Taylor series and consider where they converge and what that means. And so those are things that we're heading toward. Right now, we just want to know the definition. And you're also going to get practice with being able to find the Taylor series at any particular center for lots of different functions.